If I told you that there was a moment in Earth's history when life took one of its boldest and most revolutionary leaps, a forgotten period, overshadowed by the age of the dinosaurs, where such radical transformations occurred that they forever changed the destiny of our planet? Dear Time Explorer, today we embark on an extraordinary journey to one of the most fascinating and least known chapters in Earth's geological history, the Silurian. An age when life conquered dry land, when modern oceans took shape, and when the foundations of the ecosystems we know today were laid. A story of evolutionary courage, biological innovation, and planetary conquest. Imagine a world where the continents are arranged in unrecognizable ways, where the seas are the absolute kingdom of armored creatures, and where the first forms of life dare to leave the water to colonize virgin, desolate lands. A crucial turning point in which our planet shifted from being a purely aquatic world to becoming the vibrant mosaic of terrestrial and marine ecosystems that defines modern Earth. On this voyage, we will discover how the first land plants arose, how the earliest arthropods evolved to walk on solid ground, and how Silurian oceans teemed with a diversity of life that rivaled any modern ecosystem. And before we dive into the depths of time, don't forget to leave your like and subscribe to the channel so you don't miss any marvel of life's history. Thank you, and let the journey begin. The Earth before the Silurian, the legacy of the Ordovician. To understand the magnificence of the Silurian, we must first travel a bit further back in time, to the end of the Ordovician period, around 445 million years ago. The Ordovician had been an era of extraordinary diversification of marine life, known as the Great Ordovician Biodiversification Event, when the oceans filled with an astonishing variety of trilobites, brachiopods, mollusks, echinoderms, and the first vertebrates with rudimentary jaws. Ordovician seas were warm and shallow, covering vast stretches of the continents. Primitive coral reefs, built by tabulate and rugose organisms, along with bryozoans and sponges, formed complex structures that hosted a diversity of life comparable to modern reefs. Cephalopods, ancestors of octopuses and squids, dominated as predators. Their straight or curved shells could reach several meters in length. Nautiloids patrolled the waters with tentacles and horny beaks, while graptolites, colonial organisms floating in surface waters, formed dense colonies that filtered plankton. But the end of the Ordovician was marked by one of the most devastating mass extinction events in Earth's history. The Ordovician-Silurian mass extinction, also known as the Hernantian extinctions. This event, occurring in two main pulses, roughly 445 to 443 million years ago, wiped out about 85% of all marine species, making it the second most severe mass extinction in terms of biodiversity loss. What caused this biological catastrophe? The main driver was a rapid and severe climate shift triggered by a massive glaciation. For millions of years, the supercontinent Gondwana had been drifting slowly toward the South Pole. When it finally settled over the pole, conditions became favorable for the formation of enormous ice sheets. This glaciation was rapid in geological terms, unfolding over just a few million years, and its consequences were catastrophic. As the ice sheets expanded, sea levels dropped dramatically, estimated at more than 100 meters. Vast epicontinental seas, those shallow seas that flooded the continents and hosted most marine biodiversity, drained away. Marine habitats shrank drastically, compressing biological communities into ever smaller spaces and intensifying competition for scarce resources. At the same time, global temperatures fell sharply. Ocean waters that had been warm and stable throughout the Ordovician cooled rapidly. This thermal shock proved lethal to many species adapted to tropical conditions, especially reef builders such as tabulate and rugose corals, and brachiopods that depended on stable environments to thrive. The second extinction pulse occurred when the ice sheets began to melt. The rapid warming and rising sea levels that followed created anoxic conditions in deeper oceans. Cold, dense meltwater sank to the seafloor, stirring up accumulated nutrients and organic matter. This fueled massive blooms of algae and bacteria that consumed dissolved oxygen, creating dead zones where aerobic life could not survive. Bottom-dwelling organisms, those living on or within the seafloor, were especially vulnerable. Trilobites, which had been extraordinarily diverse in the Ordovician, suffered enormously, losing many families and genera. Graptolites, though resilient, also experienced significant extinctions. Brachiopods, the dominant filter feeders, saw their diversity slashed. Nautiloid cephalopods, the great predators of the Ordovician, also took heavy losses. And yet, as so often happens in the history of life, extinction was not the end. It was the prelude to a rebirth. The survivors of this catastrophe found themselves in a transformed world, with empty ecological niches and new evolutionary opportunities. The stage was set for the Silurian, a period when life would not only recover, but take some of its boldest and most innovative steps toward conquering entirely new realms. The question then is, how did life respond to this challenge? And what secrets does the Silurian reveal about adaptation and resilience? Welcome to the Silurian, a world in transformation. The Silurian period spanned from about 443 to 419 million years ago, roughly 24 million years of geological history. Though relatively brief compared to other periods, the Silurian witnessed fundamental changes that reshaped Earth's biosphere in ways that still echo today. Earth's geography during the Silurian was radically different from the present. The supercontinent Gondwana, comprising what are now South America, Africa, Antarctica, Australia, India, and parts of Asia, dominated the southern hemisphere, stretching from the equator to beyond the South Pole. To the north, separated by the vast Iapetus Ocean, lay several smaller continents: Laurentia, roughly modern North America; Baltica, northern Europe; Avalonia, parts of Western Europe; and Siberia as an independent landmass at northern latitudes. These continents were not static. They were in constant motion due to plate tectonics. During the Silurian, a major tectonic event was underway: the gradual closure of the Iapetus Ocean. Baltica and Avalonia moved toward Laurentia, a process that would culminate in the Devonian with the Caledonian orogeny, forming major mountain belts in Scandinavia, Scotland, and the northern Appalachians. This convergence not only reshaped geography, it also had profound implications for ocean circulation, climate, and the distribution of species. The Silurian climate was generally warmer and more stable than the late Ordovician. After the dramatic glaciation that drove the Ordovician extinctions, ice sheets retreated and global temperatures rose. Conditions became broadly temperate to subtropical, even at high latitudes, with less thermal contrast between equator and poles than today. There were no permanent polar ice caps, and sea levels were high, with vast epicontinental seas once again flooding large areas of the continents. This climatic stability was crucial for life's recovery and diversification after mass extinction. Warm, shallow seas provided ideal habitats for the resurgence of coral reefs, brachiopod communities, and a renewed explosion of marine invertebrate diversity. Atmospheric oxygen was gradually increasing, though still significantly below modern levels, around 14% compared to today's 21%. This rise in oxygen would be essential for enabling terrestrial organisms to breathe. Outside water, Silurian oceans were clear and bright, lit by a sun that would have seemed slightly dimmer than today, because our star was about 4% less luminous around 440 million years ago. The waters were rich with life, from photosynthetic microorganisms at the base of food webs to large predators lurking in deeper zones. But perhaps the most revolutionary events of the Silurian did not occur in the oceans, but at the boundary between water and land. Until this point, dry land had remained largely sterile, an eroded, wind-blasted rocky desert with no vegetation to soften its bare surfaces. The only terrestrial inhabitants were microorganisms forming biological crusts on rocks and damp soils, along with perhaps a few primitive arthropods that ventured briefly out of the water. During the Silurian, that would change. For the first time in Earth's history, plants began to colonize dry land permanently. soon followed by animals. This double conquest of the terrestrial environment ranks among the most consequential events in life's history, comparable in importance to the origin of life itself or the evolution of oxygenic photosynthesis. It would reshape Earth's surface, create new ecosystems, alter global climate, and set the stage for flowering plants, insects, dinosaurs, mammals, and ultimately, humans. How was this conquest possible? What evolutionary innovations allowed life to abandon the safety of water and confront the extreme challenges of land? To answer these questions, we must plunge into the early Silurian seas and witness the explosive marine recovery that laid the groundwork for everything that followed. The recovery of the oceans, the marine renaissance. After the devastating end Ordovician extinctions, early Silurian oceans became worlds of opportunity. Vacant niches and reduced competition allowed survivors to diversify rapidly in a phenomenon known as adaptive radiation, one of the clearest demonstrations of life's ability to rebound after catastrophe. Reefs were among the first ecosystems to recover. Tabulate and rugose corals, having suffered heavy losses, began rebuilding complex reef structures. These Silurian reefs were vibrant ecosystems, comparable in complexity to modern coral reefs, though built by very different organisms. Tabulate corals formed tabular or columnar frameworks, while rugose corals, solitary or colonial, displayed deep radial grooves in their skeletons. Around them flourished stromatoporoids, calcareous sponges that contributed massively to reef construction, forming spherical or layered masses that could reach several meters across. Brachiopods staged a spectacular comeback. These animals, superficially resembling clams but belonging to a distinct group, dominated Silurian seafloors. Unlike bivalves, brachiopods have dorsal and ventral shells rather than left and right. They were filter feeders, extending a lopophore, an array of ciliated tentacles, to capture suspended food. Particles. During the Silurian, brachiopod diversity reached extraordinary levels, with hundreds of genera adapted to different depths, substrates, and current regimes. Trilobites, though they never fully regained their Ordovician peak diversity, remained important members of marine communities. These armored arthropods, with segmented bodies and calcite compound eyes, were mostly detritivores and scavengers feeding along the seafloor. Some Silurian trilobites evolved elaborate spines and ornamentation, perhaps for defense against predators or to stabilize themselves in sediment. But perhaps the most significant development in Silurian seas was the explosive diversification of fish. Vertebrates, which first appeared in the Cambrian as small, jawless creatures, underwent an evolutionary revolution in the Silurian. Ostracoderms, jawless fish covered in bony armor, proliferated in both marine and freshwater environments. They fed by filtering sediment or ingesting particles from the seafloor. Their flattened bodies and armored plates protected them from invertebrate predators. The most transformative innovation, however, was the evolution of jaws. In the Silurian, the first gnathostomes, jawed vertebrates, appeared and revolutionized marine ecology. Jaws, derived from the front gill arches, allowed these fish to bite, chew, and process food in ways earlier vertebrates could not. This opened new ecological niches and turned vertebrates into efficient predators. Acanthodians, the so-called spiny sharks, were among the earliest jawed fish to appear. They were small, typically under 20 centimeters, streamlined, covered in tiny scales, and equipped with robust spines preceding their fins. They were active predators, feeding on small invertebrates and likely smaller fish. Placoderms, another early jawed fish group, also emerged in the Silurian, though they would reach their greatest diversity in the Devonian. They wore articulated bony plates, especially around the head and pectoral region, forming impressive armor. Some would evolve jaws with sharp bony edges acting like teeth, making them formidable predators. Eurypterids, sea scorpions, deserve special mention, though not fish but chelicerate arthropods related to modern scorpions and spiders. Eurypterids were apex predators in many Silurian aquatic environments. Some giants exceeded 2 meters in length, making them the largest arthropods that ever lived. They had segmented bodies, and their front appendages could be modified into powerful pincers or paddle-like limbs for swimming. Their chitinous exoskeleton provided both protection and structural support. Eurypterids were versatile hunters. Some likely fed on soft-bodied prey, while others possessed massive claws capable of crushing shells and exoskeletons. They inhabited marine, brackish, and freshwater habitats, serving as super predators across many ecosystems. Their presence would have been terrifying to smaller fish and other animals, forming complex food webs in which jawed vertebrates began competing with giant arthropods for dominance. Cephalopods, the top predators of the Ordovician, remained important in Silurian seas, though extinctions had reduced their diversity. Nautiloids, with straight, curved, or coiled shells, were efficient swimmers using jet propulsion. They regulated buoyancy by adjusting gas within shell chambers, enabling hunting at multiple depths. Their tentacles, armed with small hooks, captured fish and other marine animals. Crinoids, sea lilies, also underwent a notable radiation. These echinoderms, related to starfish and sea urchins, anchored to the seafloor via flexible stalks and extended feathery arms to capture food drifting in currents. In some regions, they formed true underwater forests, creating structurally complex habitats that sheltered many smaller organisms. In essence, Silurian oceans were a crucible of evolutionary innovation. Recovery from mass, extinction was not merely a return to the old status quo. It was a fundamental reorganization of marine ecosystems. Jawed vertebrates began their long rise toward dominance, while classic invertebrates such as brachiopods and corals reached new peaks of diversity. The marine stage was set, but the true Silurian revolution was about to unfold somewhere utterly unexpected, along the barren, lifeless shores of the continents. The conquest of land, the first plants. The transition from aquatic to terrestrial life is among the most monumental events in Earth's history. For hundreds of millions of years, life had been confined to oceans, lakes, and rivers. Dry land was hostile, little protection against ultraviolet radiation, scarce accessible water, extreme temperature swings, and soils poor in nutrients. To colonize this environment, life needed radical innovations. The first to take this audacious step were plants. Before true land plants appeared, green algae living near shorelines in freshwater environments began adapting to periodic exposure to air. These algae, ancestors of all modern land plants, belonged to a group known as charophytes. In temporary ponds, intermittent streams, and lake margins, they endured desiccation and developed adaptations for surviving outside water. The earliest true land plants appeared in the late Ordovician, but it was in the Silurian that they began to diversify and reshape terrestrial landscapes. These pioneer plants were extremely simple compared to modern flora, yet they possessed the essential innovations that made permanent land life possible. The oldest well-preserved land plant fossils come from the early Silurian, around 430 to 425 million years ago. These plants belong to a group known as bryophytes, non-vascular plants ancestral to modern mosses, liverworts, and hornworts. But the plants that truly marked the beginning of significant terrestrial vegetation were early vascular plants, known as tracheophytes. The genus Cooksonia is perhaps the most famous of these pioneers. Cooksonia was tiny, rarely exceeding a few centimeters in height. It had no leaves, roots, or flowers. Its structure was astonishingly simple, repeatedly branching green stems ending in sporangia, kidney-shaped structures where spores were produced. The stems contained primitive vascular tissue, xylem to transport water and phloem to distribute nutrients, an evolutionary breakthrough that allowed these plants to grow upright and move water from the substrate to aerial tissues. Another important genus was Baraguanathea, a more advanced vascular plant from the late Silurian that possessed leaf-like structures, small scale-like appendages covering its stems. Baraguanathea represents a step forward in structural complexity, showing how rapidly land plants were evolving toward more elaborate forms. These primitive plants faced formidable challenges. The greatest was desiccation. Outside water, relentless evaporation threatened to dry their tissues completely. To counter this, they evolved a waxy cuticle, an impermeable layer that reduced water loss, but the cuticle also blocked gas exchange necessary for photosynthesis. The evolutionary solution was the development of stomata, tiny pores that could open and close, allowing carbon dioxide to enter while minimizing water loss. Another challenge was structural support. In water, buoyancy provides support. On land, plants needed rigidity to stand upright. The evolution of lignin, a complex polymer that strengthens cell walls, was crucial. Lignin allowed plants to grow taller, compete for sunlight, and eventually formed the planet's first forests. Reproduction required adaptation too. Aquatic plants rely on water to disperse gametes, but on land, this strategy was difficult. Early land plants retained a life cycle requiring water for sexual reproduction, much like modern mosses. They produced spores dispersed by wind. When spores germinated in damp places, they formed gametophytes that still needed water so sperm could swim to eggs. This dependence meant early plants remained tied to moist habitats near water. Despite these limits, Silurian plants began transforming terrestrial landscapes profoundly. Their primitive root-like structures, rhizoids in simpler plants, penetrated and broke down rock, contributing to the formation of the first true soils. Dead plant material accumulated and enriched these soils, creating a more hospitable substrate for future plant generations. Terrestrial vegetation also affected global climate. Plants absorb carbon dioxide during photosynthesis, and when they die and are buried, that carbon can be sequestered rather than returned to the atmosphere. In the late Silurian, this process began gradually reducing atmospheric CO2, effects that would become stronger later. Vegetation also altered runoff and erosion, changing how water and sediments moved from continents to oceans. But plants did not colonize land alone. Fossil evidence suggests they formed symbiotic associations with fungi very early on. Mycorrhizal fungi, which form mutualistic partnerships with plant roots, likely helped early plants absorb water and nutrients from nutrient-poor soils. In exchange, plants provided sugars produced by photosynthesis. This partnership was so successful that most modern land plants still maintain it. Fungi themselves were early land colonizers. Late Ordovician and Silurian fungal fossils show complex hyphae and spores, indicating they were already well established in terrestrial environments. Fungi played a vital role as decomposers, breaking down dead organic matter and recycling nutrients, functions they still perform today. By the Middle and Late Silurian, vascular plant diversity increased. Primitive lycophytes emerged, plants that would later evolve into tree-sized forms in the Devonian and Carboniferous. Plants grew taller, developed more elaborate root systems, and occupied a wider range of terrestrial habitats. This botanical conquest set the stage for the next great leap, animals moving onto land. Once plants built terrestrial ecosystems, they provided food and shelter, creating ecological niches for animals to exploit. So the question becomes, who were the first animals to follow plants out of the water? And how did they survive in an environment so radically different from the oceans that had been their home for hundreds of millions of years? The first invaders, arthropods on dry land. If plants were the pioneers of land colonization, arthropods were the first animals to follow. With their chitinous exoskeletons and segmented bodies, arthropods were pre-adapted for terrestrial life in ways other animals were not. The exoskeleton provided structural support outside water and offered protection against desiccation, though it needed modification to enable air breathing. Fossils and trace evidence suggest arthropods began venturing out of water as early as the Ordovician, but it was during the Silurian that they became permanent terrestrial residents. The earliest land arthropods were likely small creatures resembling modern myriapods, exploring damp shorelines to feed on detritus, decaying organic matter, and microorganisms. One of the most important fossils for understanding this transition is Pneumodesmus pneumani, discovered in Silurian rocks of Scotland dating to about 428 million years ago. This fossil represents the oldest known terrestrial myriapod, and most importantly, it possesses spiracles, openings in the exoskeleton leading to a tracheal system, branching tubes that deliver air directly to tissues. Spiracles are a clear adaptation for air breathing, providing unambiguous evidence that Pneumodesmus was a true land animal. Myriapods, including millipedes and centipedes, were likely among the first arthropods to establish permanently on land. Early millipedes were detritivorous, feeding on decaying plant, material, fungi, and microbes in the soil. Their role as decomposers was crucial for nutrient recycling in these early terrestrial ecosystems. Centipedes, in contrast, were predators, hunting other small arthropods with venomous claws. Arachnids, the group including spiders, scorpions, mites, and harvestmen, also appeared during the Silurian. Scorpions are particularly fascinating because they show a clear transition from water to land. The earliest scorpions were aquatic, living in marine or freshwater habitats and breathing through gills. During the Silurian, some began modifying these gills into book lungs, folded structures that increased surface area for gas exchange in air. Silurian and Devonian scorpions show a mix of aquatic and terrestrial features, suggesting a gradual transition. Paleophanus, a Silurian scorpion genus, likely spent time both in water and on land. It had a venomous stinger like modern scorpions, indicating it was already an efficient predator. These early scorpions hunted other arthropods in aquatic environments and along damp shorelines, helping establish the first terrestrial food webs. Trigonotarbids, extinct arachnids related to spiders but lacking silk glands, also appeared in the late Silurian. They were small predators, about coin-sized, stalking through low vegetation and leaf litter, feeding on springtails, mites, and other tiny arthropods. Springtails, colembolans, tiny hexapod arthropods incredibly abundant in modern soils, were probably among the earliest land colonizers as well. Their fossils are rare due to size and fragility, but their ancestors were likely present in terrestrial habitats by the Silurian, feeding on fungi, algae, and detritus. Life on land required major physiological adaptations beyond respiration. Terrestrial arthropods needed to avoid dehydration, regulate body temperature amid greater fluctuations than in water, and excrete waste while conserving water. Many evolved a waxy cuticle over their exoskeleton to reduce water loss, similar to the cuticle of plants. Locomotion also differed. Without buoyancy, arthropods needed sturdier limbs and a lower center of gravity. Myriapods developed many pairs of legs to distribute weight, while arachnids refined efficient movement with 8 legs adapted to uneven terrain. Evidence for this early terrestrial invasion comes not only from body fossils, rare due to fragility, but also from trace fossils. Footprints, burrows, and trackways preserved in ancient Silurian soils reveal arthropod activity. Some traces indicate complex behaviors, such as burrowing to avoid dehydration and predators. Arthropod colonization had cascading effects on both land and water ecosystems. On land, arthropods acted as decomposers, recycling nutrients and promoting soil development. They also established the first terrestrial food webs, including herbivores, detritivores, predators, and parasitoids. When these animals died or returned to water, they carried nutrients that enriched aquatic systems. Yet Silurian terrestrial ecosystems were extremely simple by modern standards. There were no large plants providing vertical structure, no trees, no shrubs, only low mats of vegetation. Arthropods were small, mostly millimeters to centimeters long. There were no land vertebrates, no flying insects, no flowers, no seeds. It was a world in its earliest stages, but one laying the foundation for all later complexity. The true explosion of terrestrial diversity would occur in the Devonian, when plants evolved tree-sized forms, insects appeared and diversified dramatically, and the first vertebrates made tentative steps onto land. But all of that was only possible because of the Silurian pioneers, plants and arthropods, that dared to abandon the security of water and conquer a new and challenging world. The jaw revolution, the rise of fish, while plants and arthropods were writing the first chapters of life on land, and equally, transformative revolution was unfolding in the oceans, the rise of jawed vertebrates. This evolutionary event beginning in the late Ordovician but accelerating dramatically in the Silurian, permanently changed aquatic ecosystems and ultimately led to terrestrial vertebrates, amphibians, reptiles, birds, mammals, and humans. To grasp the magnitude of this innovation, consider the limitations of jawless vertebrates. Agnathans, like the ostracoderms that dominated Ordovician and early Silurian waters, lacked structures for biting or grasping. They fed mainly by filtering sediment, sucking up particles from the bottom, or filtering small organisms. Some developed hardened mouth plates for scraping algae or detritus, but their ability to process food was limited. Jaws changed everything. They allowed vertebrates to bite, slice, crush, and grip, opening vast new feeding strategies. Jawed fish could become efficient predators, actively hunting other animals, including other fish. They could feed on hard-shelled invertebrates by crushing defenses with robust teeth. They could tear algae from rocks or rip apart large prey. This flexibility was central to their evolutionary success. But how did jaws evolve? Anatomical and embryological evidence indicates jaws evolved from gill arches, the bony or cartilaginous supports of gills. In jawless fish, a series of gill arches extends behind the skull. Sometime in the late Ordovician, in a lineage of early vertebrates, the first pair of arches modified and shifted forward, fusing with the skull to become upper and lower articulated jaws. The second pair modified into the hyomandibular, a structure supporting jaw articulation. This transformation required major cranial reorganization. Muscles that once operated gills were repurposed to open and close jaws. Teeth evolved, likely from modified dermal scales, to equip jaws with cutting edges or crushing surfaces. The earliest jawed vertebrates appear in the fossil record in the late Ordovician, but it was during the Silurian that they truly diversified. Acanthodians, already mentioned, were among the first to thrive. Small, agile fish occupying niches similar to many small modern fish, feeding on zooplankton, small invertebrates, and perhaps occasionally cannibalizing. Placoderms, the other major jawed fish group of the Silurian, displayed a different body plan. They were heavily armored with articulated bony plates covering head and thorax. Their jaws were unique. Rather than replaceable teeth, they had sharp bony edges functioning like blades. Some later placoderms would evolve tremendous bite forces rivaling modern crocodiles. In the Silurian, placoderms were relatively small and likely mid-sized predators, hunting smaller fish, trilobites, and other invertebrates. Their armor protected them from eurypterids, giant sea scorpions still dominating many aquatic habitats. But acanthodians and placoderms were not the only jawed fish lineages emerging in this era. Somewhere in the Silurian, or perhaps earlier, two lineages originated that would come to dominate waters worldwide. The chondrichthyans, sharks, rays, chimeras, and the osteichthyans, bony fish. Chondrichthyans, with cartilaginous skeletons and rough placoid scales, were efficient predators from their earliest stages. Early Silurian and Devonian sharks were small compared to many modern relatives, but already had the traits that would ensure success. Jaws with multiple rows of replaceable teeth, streamlined bodies, and keen senses, including the lateral line to detect vibrations and ampullae of Lorenzini to sense electric fields. Osteichthyans, bony fish, are today the most diverse vertebrate group with over 30,000 species. In the Silurian, they were still primitive, but they already showed defining traits: bony internal skeletons, bony scales, and a swim bladder, an internal gas-filled organ that controls buoyancy. Osteichthyans split early into two great branches: actinopterygians, ray-finned fish, and sarcopterygians, lobe-finned fish. Ray-fins include most modern fish, with fins supported by radiating bony spines. Lobe fins, in contrast, have fleshy fins with internal bony supports, and this group includes not only modern coelacanths and lungfish, but also all terrestrial vertebrates, amphibians, reptiles, birds, and mammals. During the Silurian, sarcopterygians began exploring freshwater environments. Some developed primitive lungs, modifications of the swim bladder, allowing them to breathe air. This was crucial because many Silurian and Devonian freshwater habitats were seasonal swamps and ponds that became oxygen-poor during warm months. Air breathing provided a major advantage in those conditions. The importance of jawed fish in the Silurian cannot be overstated. They reorganized aquatic food webs. Vertebrates, once mostly low-level consumers in the Cambrian and Ordovician, became mid- and top-level predators. They began competing, with eurypterids and cephalopods for dominance. This competition fueled an evolutionary arms race. Fish evolved faster swimming speeds, sharper senses, and more complex hunting strategies. Invertebrates responded with stronger defenses, thicker shells, spines, faster burrowing, and improved sensory systems to detect predators. In this sense, the Silurian was an era of massive evolutionary experimentation in the oceans. Its successes and failures established patterns that would shape aquatic life through the rest of the Paleozoic and beyond. When the Silurian gave way to the Devonian, the age of fishes, vertebrate diversity and complexity would explode in ways that transformed the biosphere. But all of that began with the Silurian jaw revolution. The end of the Silurian, setting the stage for the Devonian. As the Silurian drew to a close around 419 million years ago, Earth was a transformed planet. In just 24 million years, life had taken some of its boldest steps, conquering new territories and pioneering innovations that would redefine the biosphere. Continents that had been widely separated at the start of the Silurian were now drawing closer. The Iapetus Ocean narrowed as Baltica and Avalonia converged with Laurentia. This collision, culminating in the early Devonian, produced the Caledonian orogeny, uplifting vast mountain ranges stretching from Scandinavia through Scotland to the northern Appalachians. These mountains altered regional climates and fed new sediment into oceans, creating new habitats both marine and terrestrial. Late Silurian climate remained generally warm and stable, though evidence suggests brief and localized cooling intervals. Sea levels began to fluctuate modestly, creating new coastal and nearshore habitats. The atmosphere continued evolving as land plants contributed to a gradual rise in oxygen. Though still well below modern levels, this added oxygen would be crucial in the Devonian for larger, more active arthropods. Terrestrial ecosystems, though still primitive, were firmly established. Vascular plants formed vegetated mats along coasts and river margins and began spreading inland. The first true soils, enriched with organic matter, supported denser plant communities and provided habitats for growing arthropod diversity. Fungi and microorganisms flourished in these soils, decomposing organic matter and recycling nutrients. In the oceans, life reached new peaks of diversity. Silurian reefs rivaled modern reefs in complexity, though built by different organisms. Jawed fish were now established as key members of aquatic food webs, even as eurypterids and cephalopods remained major predators. Trilobites persisted in specialized niches, though reduced in diversity. Brachiopods continued dominating seafloors, filtering water, and contributing significantly to benthic biomass. One of the most fascinating aspects of the late Silurian is how it set the stage for even more dramatic changes in the Devonian. Silurian vascular plants were small and simple, but their Devonian descendants would include the first true trees, forming Earth's first forests. Silurian terrestrial arthropods were primitive, but in the Devonian, the first insects would appear and diversify, eventually giving rise to flying forms. Silurian fish began exploring freshwater environments, but in the late Devonian, around 375 million years ago, lobe-finned fish would make the leap onto land as the first tetrapods, ancestors of all amphibians, reptiles, birds, and mammals. The Silurian to Devonian transition was relatively smooth, lacking a major mass extinction, especially compared to the dramatic beginning of the Silurian after Ordovician extinctions. Still, minor extinction events near the end of the Silurian affected primarily graptolites and some brachiopods and trilobites. These appear linked to sea level changes and possible ocean anoxia episodes when deep waters became oxygen poor, a recurring phenomenon throughout the Paleozoic. The Silurian offers powerful lessons about resilience. After the end Ordovician crisis, life not only recovered, it innovated in profound ways. The evolution of land plants and arthropod colonization represent some of the most important ecological transitions in Earth history. The diversification of jawed fish established vertebrate dominance patterns that persist today. These events remind us that evolutionary crises, though devastating, can also create opportunities for innovation. Empty niches can be filled by survivors that diversify rapidly, exploring new adaptations and strategies. The Silurian exemplifies this process, showing that life can rebound from catastrophe and reach new levels of complexity. It's also crucial to recognize how much of the modern world has roots in the Silurian. The forests that would eventually blanket continents began as humble Silurian plant carpets. The insects that pollinate plants and underpin countless food webs descend from early terrestrial arthropods. The fish in our seas, rivers, and lakes, and the land vertebrates that dominate Earth trace back to jawed fish that evolved during the Silurian. The Silurian legacy, revolutions that changed Earth. The Silurian, though often overshadowed in popular imagination by more dramatic periods, like the Cambrian with its explosion of forms, or the Cretaceous with its giant dinosaurs, represents a decisive turning point in Earth's history. Transformations during these 24 million years echoed across all subsequent geological time and still shape our world today. The colonization of land by plants was perhaps the most transformative event. Before the Silurian, dry land was essentially sterile, a rocky desert without visible life. Silurian plant pioneers began a process that would eventually turn continents into the vibrant terrestrial ecosystems we know. This colonization triggered cascading effects that fundamentally altered Earth's system. First, plants transformed the atmosphere. Through photosynthesis, they absorbed carbon dioxide and released oxygen. During the Silurian, this began a gradual oxygen increase that continued into the Devonian and peaked in the Carboniferous, when oxygen levels exceeded 30%, enabling giant arthropods, dragonflies the size of hawks and myriapods over 2 meters long. Plant-driven carbon sequestration also influenced global climate. Carbon removed from the atmosphere and locked into plant tissues could, when buried, be removed from the carbon cycle for long intervals. This eventually contributed to global cooling episodes, though these effects became fully pronounced later. Second, plants initiated the formation of true soils. Before land plants, soils were mostly weathered rock with little structure or organic content. Plant root systems penetrated and fragmented rock, accelerating chemical and physical weathering. Dead plant matter accumulated, supporting fungi, bacteria, and detritivorous arthropods. Over time, these processes produced rich, complex soils capable of sustaining diverse ecosystems. Soil formation also affected the oceans. Soils retain water, reducing surface runoff and erosion, but they also release nutrients via rivers to the sea. During the late Silurian and Devonian, increased nutrient runoff likely contributed to eutrophication events, algal blooms that consumed oxygen as they decomposed, creating marine dead zones. Third, vegetation altered the hydrological cycle. Plants transpire water, releasing moisture into the atmosphere and increasing precipitation over land, making continental climates less arid. Vegetation also reduced erosion, stabilizing soils and changing sediment transport from continents to oceans. Arthropod conquest of land established the first terrestrial food webs and paved the way for vertebrate colonization. Terrestrial arthropods acted as decomposers, herbivores and predators, creating nutrient and energy circuits, connecting vegetation to soil. When vertebrates later moved onto land in the Devonian, they encountered ecosystems already established and ready to exploit. The evolution of jaws in vertebrates had equally profound implications. It turned vertebrates from low-level consumers into versatile predators capable of exploiting many resources. Jawed fish diversified explosively, giving rise to two major lineages that dominate today: chondrichthyans, sharks and rays, and osteichthyans, bony fish. Within osteichthyans, sarcopterygians, lobe-finned fish, evolved adaptations for low-oxygen freshwater environments. primitive lungs allowed air breathing, an adaptation that later facilitated terrestrial life. In the late Devonian, around 375 million years ago, Sarcopterygians evolved into the first tetrapods, four-limbed vertebrates able to move on land. These tetrapods gave rise to all amphibians, reptiles, birds, and mammals, including humans. It is astonishing to realize that every terrestrial vertebrate that has ever lived, from the first Devonian amphibians to the dinosaurs, from Ice Age mammoths to modern humans, descends from those Silurian jawed fish that began exploring freshwater worlds. The Silurian also reveals how interconnected Earth's systems are. Events in one realm, like plant colonization of land, triggered cascading impacts on atmosphere, climate, oceans, and evolution in both marine and terrestrial ecosystems. This means we cannot fully understand any part of Earth's system in isolation. We must consider the feedback loops linking geology, air, oceans, and life. From a modern perspective, studying the Silurian also helps us understand how ecosystems respond to disturbance. The end Ordovician extinctions and subsequent Silurian recovery provide a natural case study in resilience. Life's rapid rebound and diversification suggest the biosphere can reorganize after perturbations, though the outcome may differ greatly from what came before. Still, resilience has limits. Ordovician extinctions eliminated about 85% of species. Some lineages never fully recovered. Trilobites, for example, never returned to their mid-Ordovician diversity and continued declining until their final extinction at the end of the Permian 250 million years later. The Silurian also reminds us that geological and evolutionary change can occur at very different tempos. Some transitions, like land colonization, happened relatively quickly in geological terms, with early plants diversifying in just a few million years. Other processes, like continental drift and mountain building, operate over tens to hundreds of millions of years. Understanding these timescales is essential for interpreting the geological record and predicting how Earth systems may respond to future change. Conclusion: the Silurian, a forgotten yet fundamental era. We have completed our epic journey through the Silurian, an era less famous than others, yet absolutely vital in shaping the Earth we know today. From the depths of Silurian oceans, where jawed fish began their rise toward dominance, to damp shorelines where the first plants clung to bare rock, the Silurian was a world of pioneers and evolutionary revolutionaries. The lessons of the Silurian echo through time. They show us that life is astonishingly resilient, capable of recovering from devastating catastrophes and innovating in entirely new directions. They teach us that major ecological transitions, like colonizing land, do not happen instantly, but through incremental steps, with each generation building on the adaptations of the last. The Silurian also reminds us of our deep connection to deep time. Every breath we take depends on oxygen produced by plants, a legacy that began with those first Silurian land plants. The soils that feed our crops and support forests formed through processes initiated in the Silurian. The vertebrates that populate our world, from fish in the sea to birds in the sky and mammals on land, descend from Silurian jawed fish. As you reflect on this documentary, consider the extraordinary journey of life on our planet. The Silurian may not have the fame of the Cambrian or the Cretaceous, but its importance is undeniable. It was the age when life made some of its boldest leaps, when irreversible thresholds were crossed, when new worlds of evolutionary possibility opened. The next time you walk through a forest, look at the plants around you and remember that their distant ancestors were the brave pioneers of the Silurian. When you see a fish swimming in a stream, recognize that it carries the heritage of jaws that evolved more than 400 million years ago. When you breathe deeply, give thanks to Silurian plants that began the long process of oxygenating our atmosphere. The Silurian teaches us that change is the only constant in Earth's history, and that life, in its infinite creativity, always finds ways to adapt, innovate, and thrive. It is a testament to the power of evolution and to the ability of organisms to transform not only themselves, but the planet itself. If this journey to the Silurian captivated you, don't forget to subscribe so we can keep exploring the mysteries of deep time together. Every geological period has extraordinary stories to tell, secrets waiting to be revealed. The history of life on Earth is a 3.8 billion year epic filled with drama, innovation, catastrophe, and triumph. And we've only just begun to uncover its wonders. Thank you for joining me on this voyage into the Silurian, the forgotten period that changed Earth forever. See you in the next adventure through time.